Continue our discussion about linear independence and dependence because it's such an important topic. Alright, so now in the last video we learned what is it mean to be linearly independent and linearly dependent, and we gave a definition also. But really, even though we know that two functions are linearly dependent if they are constant copies of each other, constant multiples of each other, or and when you are given a lot of functions, you might be not able to use that definition, use this idea about constant copies to determine whether the given set is linearly dependent or not, because sometimes functions can be complicated. So definitely we need to have a method of figure outing linear independence and dependence. So the method comes really from the definition. So what is the definition said? Well, here for example two functions are given. Okay, so what I do is I take the linear combination. That means multiply the first function by a constant c1 times 3x plus multiply the second function also by a constant c2. Okay, and let's make it equal to 0. Now how do you get linear independence? Now these two functions are linearly independent if you get c1 and c2 both be 0, both, right? So that means you have no way of combining 3x and 6 square plus 1 to get 0 other than these two coefficients being 0, right? Okay, so we use exactly the same idea. Now what we are going to do is we are going to solve for c1 and c2. That's the method. So let me show you how we can do that. Okay, so let's rewrite this 3xc1 plus let's distribute this c2, 6x square c2 plus c2 times 1 here is c2. Okay, so let's regroup these terms. So I would give the priority to x square term, so it look like a polynomial. 6x square c2 plus 3x c1 and then c2 is equal to 0. So now we have an equation. Now we want to solve for c1 and c2. You have two unknowns, but really you have a one equation. How do you solve it? Solve this equation for c1 and c2. Let me show you how. On the right hand side we have 0, right? So on the left hand side we have a polynomial, a second degree polynomial. Now let's write the right hand side also as a second degree polynomial. We have on the left hand side we have a second degree polynomial. Let's figure out a second degree polynomial on the right hand side, which is actually 0x square plus 0x plus 0, right? Because that is how you get 0. You can imagine you had x square and x and constant terms, because you multiply them by 0, eventually you get 0, right? This means 0. Okay, now what we do is we compare the coefficients. Now look at the coefficients of x square. So here the coefficients of x square is 6c2, right, on the left. So it should match with the coefficient of the right hand side, which is 0. So this means c2 is 0, right? Now let's match the coefficients of x term. So here the coefficient of x term is 3c1 on the left, on the right 0. So c1 is 0 here. So now we can see both c1 and c2 are 0. So that means these two functions are linearly independent. So we do a coefficient comparison to solve for c1 and c2. So we get c1 and c2 both 0. Every coefficient 0, so these two are linearly independent functions. So they are not constant copies of each other. Let me show you another example because we want to learn this very well. So let's say we have a function 5x and 7x square plus 3x plus 1. A similar example, two functions, a similar example, but I want to give you another example similar to the first example just to get used to the procedure. Then in the third example I will give you a different one. Now let's take the combination, linear combination. c1 5x plus c2 7x square plus 3x plus 1 equal to 0. Okay, so now what we do is we distribute the coefficients. So here 5x c1 distribute c2, so 7x square c2, 3x c2 plus c2 is equal to 0. Now let's regroup them that look like a second degree polynomial because we have highest degree 2. 7x square c2 here. Now here we have 2x terms, right? So we can write 5x c1, 3x c2. Let's do that slowly, and we have a constant term, just a constant term c2. Now furthermore, what we can do is 7x square c2 plus, here we can take a x out, factor x out. So we can write this as 5c1 plus 3c2 times x plus c2, so that I can visibly see the coefficient of x, because I did that because I had 2x terms here. I just want it to reduce to be a 1x because we can extract the coefficient of c2 clearly. Now on the right hand side, we also assume that we have a second degree polynomial, right? So we can write it as 0x square plus 0x plus 0, because on the left hand side also you have a second degree polynomial. So let's compare the coefficients. Coefficient of x square gives you 7c2 on the left, on the right 0. So that means c2 is 0. Now let's compare the coefficients of x, okay, or you can compare the constants. So here the constant is c2, so on the right also the constant is c2, so c2 is 0. Oh, we already knew that. Okay, never mind. So let's compare the coefficients of x. So here 5c1 plus 3c2 is the coefficients of x. On the left, coefficient of x on the right is 0, but we already knew c2 as 0, so c2 times 3 is 0, 3 times 0 is 0, so 5c1 0 means c1 0, so we get both coefficients to be 0. So these two functions are again linearly independent. Okay, we can see it from without doing this, because 5x times a constant doesn't give you 7x square plus 3x plus 1, right? But I wanted to show you the method. Now let me give you an interesting example, because we saw examples where both of them were linearly independent. So let's look at this. 2x, 7x, x square plus 2x plus ex. Now right away you know this is linearly dependent. You have a linearly dependent set because these two are dependent, right, on each other, linearly dependent, because 2x can be multiplied by 7 over 2 and get 7x, right? So these two are constant copies of each other. But does it make this whole set linearly dependent? That's the question. What do you think? Yes, the set is linearly dependent. Even though only these two are dependent, you consider these three functions as a one set. Okay, inside that set you have two functions that are linearly dependent, so the whole set is linearly dependent. Okay, all right, so it's like you have a group of kids and someone say that two students of that groups are bad, so a teacher judged that the whole group is bad. It's not a fair thing, but in mathematics this is a fair argument. Okay, all right. Okay, let's prove it using our definition. Okay, I want you to show that how it works. So 2x times c1 plus c2 times 7x. Now we have a c3 come into play. X square plus 2x plus e to the x is equal to 0. Okay, all right. So let's distribute the coefficients. 2x c1, 7x c2. Let's distribute c3. X square c3, 2x c3, e to the x c3 is equal to 0. Now let's regroup them. Let me write these x square terms on in the beginning. X square c3 plus x terms 2x c1 plus 7x c2 plus 2x c3 plus then the e to the x term. Okay, furthermore I can factor x here, so I can write 2c1 plus 7c2 plus 2c3, take out an x, take out a x, and e to the x c3 is equal to 0. Alright, so now I have a clean left hand side. Okay, simplified left hand side. order, grouped better. That is what I should say. Now let's compare the coefficients. On the right, I assume that I have 0x square plus 0x plus 0 times e to the x. Because you have a e to the x here, we can have a e to the x here on the right hand side. Of course, yes, but it's multiplied by 0. So no matter what function you have, it's multiplied by 0. So right hand side is 0. So any function here, any function term here can be represented on the right hand side, because of course you can multiply that term by 0, and it does not harm anything. Okay. All right. So let's compare the coefficients. Coefficients of x square. So coefficients of x square gives me the coefficients of x square in the left is C3. On the right is of course 0. So C3 is 0. Okay. All right. So now let's compare the coefficients of x. Okay. So if you compare the coefficients of x, what we have on the left is 2c1 plus 7c2 plus 2c3. C3 is already 0. So let's not take that. And coefficient of x on the right is 0. Okay, now this does not help us to find either c1 or c2, right? We do not have enough information, so let's keep it there. But if you look at the coefficient of ex, our only other option, the coefficient of ex on the left is c3, on the right is 0. So it again confirms the fact that c3 is 0, but did not give anything new or contribute anything new to solve c1 or c2. But now, does this mean C1 and C2 are 0? Here's the question. $1 million question. C3 is 0. But does this mean C1 and C2 0? No. Okay? Because we don't explicitly get C1 and C2 to be 0. So C1 and C2 are some non-zero values, right? So for example, we can say 2C1 is negative 7C2. I can take this negative 7C2 to the right and divide by 2 here. So C1 is negative 7C2 over 2. So this is a relationship among C1 and C2, but it does not mean C1 and C2 are 0. Okay. So, and if you choose C2 to be any number you like, for example, if C2 is 1, C1 is negative 7 over 2. So since explicitly we didn't find C1 and C2 to be 0, okay, this does not mean C1 is 0, C2 is 0, C3 is 0. So C1 and C2 are in fact non-zero, can be non-zero coefficients. So this is a linearly dependent set. Because this is a linearly independent set, if we definitely get C1, C2, C3 all 0, but we didn't get that here. Okay, we were stuck here with lack of information to solve C1 and C2, but that does not mean C1 and C2 are 0. You can take any number to C2 other than 0 and it provide you a non-zero C1 and it works. Okay, so this is a linearly dependent set because C1, C2 and C3 all were not 0. Yes, C3 is 0, but C1 and C2 was not 0. So because of that, this is linearly dependent. Because if you want linear independence, you definitely need to have C1, C2, C3, all 3 0. Okay. Alright, so that is how we use the definition. And here's the secret. We are going to learn a much better method in next video. Okay. So I will see you in the next one. Thank you.